In this lecture video, we're going to be looking at example 5.1, which involves a 2x2 complete factorial treatment structure. So let's look at a description and a brief overview of the context. Suppose there are two fixed effects factors under consideration, which will be denoted as factors A and B. Suppose further that factor A consists of two levels, denoted by A1 and A2, and factor B also consists of two levels, denoted by B1 and B2. Then the complete factorial treatment structure for this situation would be called a 2x2 complete factorial treatment structure. This set of treatments consists of the 2 times 2 or 4 treatment combinations, which are denoted by A1B1, A1B2, A2B1, and A2B2. Note that every level of each factor occurs in combination with every level of the other factor, so this is indeed a complete factorial treatment structure. Now consider the effects model representation of the model, and suppose that the model effects have the following values: mu equal to 100, alpha 1 equal to 20, alpha 2 equal to negative 20, beta 1 equal to negative 40, beta 2 equal to positive 40, alpha beta 1 1 equal to negative 10, alpha beta 1 2 equal to positive 10, alpha beta 2 1 also equal to positive 10, and alpha beta 2 2 equal to negative 10. Now recall that in the means model representation of the treatment means, if the treatment means mu ij are fixed effects, then the mu ij's are unknown constants with arithmetic mean equal to mu. So mu is equal to 1/4 times the sum of the 4 treatment means. Now I've got this expressed a couple different ways here. 1/4 times the sum I going from 1 to 2 and j going from 1 to 2 of the mu ij's. I've also have this represented using the dot notation. So mu sub dot dot is the sum of all of the treatment means over all 4 combinations, and then we divide that by 4. And then I'm also on the far right hand side denoting that mean of the 4 values as mu bar dot dot. So remember that the dot in a subscript or index means that we've summed over any index that has the dot. And then if we put the bar on the top, that means that we've taken the average. Now, verify that this formula holds in this example. Now recall also that in the effects model representation, if the treatment effects alpha sub I, beta sub j, and the alpha beta ij's are all fixed effects, then the following constraints hold among the various parameters. So the first one is that the alphas sum to 0. The second constraint is that the betas sum to 0. The third constraint says that if we sum the alpha beta ij's over either of the two, or over the first index specifically, then that sums to 0. And then the final constraint says that if we add up the alpha beta ij's over the second index or subscript, that sum also equals 0. And so what I want you to do is to also verify that these constraints do in fact hold for this example. Now with those values for the effects model parameters, the treatment means the mu ij's have the following values. So mu 1 1 turns out to be equal to 70. Mu 1 2 is equal to 170. Mu 2 1 is equal to 50. And mu 2 2 is equal to 110. Now it's convenient to organize these values in a two-way table of treatment means, as we've seen in a previous lecture video, and we've done that here on the next slide. And so here we see the rows correspond to the levels of A, The columns correspond to the levels of B. And then in the individual cells, which are intersections of a row and a particular column, we've got the mean for the corresponding treatment combination. All right, next, let's calculate means and effects associated with this 2x2 complete factorial treatment structure. And we'll start off by first calculating various means of interest. So we're going to be calculating arithmetic means for each factor level and also the overall mean of the treatment combination means. Let's first calculate the row means. These are the means of the levels of factor A. Mu bar 1 dot is the mean of the values in the first row of our 2x2 table. It's the mean of the values mu11 and mu12. Those values are 70 and 170. They add up to 240. When you divide by 2, we get 120. So mu bar 1 dot is 120. Mu bar 2 dot is the mean of the treatment combinations that have the second level of factor A. It's the mean of the values in the second row of the table. Those treatment combination means are 50 and 110, and when averaged together, we get 80. All right, and so here we see the two calculations. Mu bar 1 dot, which is the mean for the row corresponding to A1, is 120. We're averaging the values 70 and 170. And then mu bar 2 dot is the mean of the treatment combinations in the row labeled A2, the second level of factor A. Those values are 50 and 110, and their average is 80. Next, we're going to calculate the column means. These are the means for the levels of factor B. Mu bar dot 1 is the mean of the values in the first column of the table. Mu11 and mu21. Those values numerically are 70 and 50, and when averaged together, we get 60. Mu bar dot 2 is the mean of the values in the second column of the table. Mu12 and mu22. Those values are 170 and 110, and they have an average of 140. And so we see here in the context of the two-way table, 60, which is mu bar dot 1, is the average of the values in the first column. It's the mean of the values corresponding to the first level of factor B. And then 140 is the mean of the values in the second column. This is mu bar dot 2, and it's the mean of the values of the second level of factor B. And then finally, we're going to calculate the overall mean, mu, and we can calculate this in really three different ways. We can calculate the mean of the column means, which is that first expression. We can calculate the arithmetic mean of the row means, which is the second expression. And we can also calculate the arithmetic mean of the four treatment means in the body of the table. That is the third expression. All right, and then we can call that not only mu, but to reinforce how we're actually calculating, we can denote this as mu bar dot dot. The bar signifying that we're taking an average, and the dot dot in the subscripts indicating that we're averaging over both I and j. And so the overall arithmetic mean of the treatment means turns out to be 100. And again, all three of these calculations return the same value. And in the context of the two-way table, we can see that we can calculate that value of 100 for the overall mean in three different ways. As the arithmetic mean of the column means, as shown here, the arithmetic mean of 60 and 140. We can also get it as the arithmetic mean of the row means, the arithmetic mean of 120 and 80. And finally, we can get this as the arithmetic mean of the four treatment means in the body of the table. All right, next, let's look at the various types of effects that we are interested in and can calculate in the context of a 2x2 complete factorial treatment structure. And so recall that in the context of a 2x2 complete factorial treatment structure, there are three types of effects. We have simple effects, of which there are 4. We have main effects. There are 2 of those. And then we have an interaction effect. Now we can think of that interaction effect in 2 different ways, but as it turns out, as we'll see, there's actually one value for the interaction between our 2 factors A and B. So let's first calculate the simple effects. So the simple effect of a factor is the difference between treatment means for 2 levels of the factor at a given level of the other factor. Now, in the notation of the means model, the simple effects are calculated as follows and as shown on this slide. So let's first calculate the simple effect of A at the first level of B. And so this is given by mu21 minus mu11. Mu21 is equal to 50, mu11 is equal to 70, and the difference is negative 20. And so we can see this in the context of the table. We're taking the difference between the 2 values in the first column of the table, and we're taking the difference 50 minus 70, and we're going to put this in a new row that we've appended to the table. And that row, we've labeled that as the simple effects of A. And we can see here that that value for the simple effect of A at the first level of B is equal to negative 20. Next, let's calculate the simple effect of A at the second level of B. This is given by mu22 minus mu12. Those values are 110 and 170 respectively, and so 110 minus 170. And that gives us the simple effect of A at the second level of B being equal to negative 60. Now we can see this in the context of the table in the same way. Here we're going to be taking the difference between the values in the second column of the table, and in the order 110 minus 170. And so that's going to give us the simple effects of A at the level B2. Next, let's calculate the simple effect of B at the first level of A. That's defined to be mu12 minus mu11. That's going to be equal to 170 minus 70, which is 100. In the context of the table, we have appended a column to the table, and we are now taking the difference of the treatment means in the first row of the table. And the difference is 170 minus 70, and so that gives us 100. And then finally, the fourth simple effect, the simple effect of B at the second level of A. That's defined to be mu22 minus mu21, 110 minus 50, which is 60. We see this in the table. We're taking the difference between the treatment means in the second row of the table and place that value in the column labeled simple effects of B, and so that's going to be 110 minus 50, or 60. So the table gives us not only a convenient way to organize the treatment means, but it also gives us a way, when expanded like this, to organize our work, organize the calculations in calculating the various means and effects. Now, in the notation of the effects model, the simple effects can be calculated in the following way. So the simple effect of A at the first level of B1 can be calculated using the formula shown here. And if we plug those values in, and remember that those values were given to us in the overview or the description of the example, we get negative 20. Using the effects model notation and values, the simple effect of A at the second level of B is negative 60. The simple effect of B at the first level of A is equal to 100 using this formula and the corresponding values. And the simple effect of B at the second level of A is equal to 60. And we can verify that those values are the same values that we got using the means model formulas as well. All right, next, let's calculate the main effects. Recall that the main effect of a factor can be defined and calculated in two different ways. The first as the arithmetic average of the simple effects of that factor, and also as the difference between the means of the two levels for that factor. Now, in the notation of the means model, the main effects are represented and calculated as follows. For the main effect of A, on the left-hand side, we have the arithmetic average of the simple effects of factor A. So mu21 minus mu11 is the simple effect of A at the first level of B. Mu22 minus mu12 is the simple effect of A at the second level of B. And so we're averaging those, and that gives us the main effect of A. Now, algebraically equivalent to that is the expression on the right-hand side, which is the difference between the means of the two levels for factor A. So mu bar 2 dot minus mu bar 1 dot. So those two expressions are algebraically equivalent and will give us the same value, but we can think of them in these two different ways. Likewise, the main effect of B can be calculated as the arithmetic average of the simple effects for B. So mu12 minus mu11 is the simple effect of B at the first level of A. The simple effect of B at the second level of A is mu22 minus mu21. And if we average those together, we get the main effect of B. Similarly, we can calculate the main effect of B as the difference between the means of the two levels of factor B. So that would be mu bar dot 2 minus mu bar dot 1. And so let's do this first for the main effect of A. We'll first calculate the main effect as the arithmetic average of the simple effects of factor A. And so we found the simple effects previously to be negative 20 and negative 60, and the average of those two values is negative 40. So the main effect of A is negative 40. Now, this value has a particular location in the two-way table. It's in the cell at the intersection of the column and row corresponding to the mean of the simple effects of A. And so we're going to be averaging the simple effects of A, negative 20 and negative 60, and putting that average into the mean column for that row. And so we see that negative 20 minus 60 over 2 is equal to negative 40. And so that's where that value would go. And that cell, therefore, gives us the main effect of A. Now, we can also calculate the main effect of A as the difference between the means of the two levels of factor A. So mu bar 2 dot minus mu bar 1 dot, which would be 80 minus 120. And that gives us, again, negative 40. Now, looking in the table, we're going to be taking the difference between the values 80 and 120 that I've got shown here in the table. And we're going to put the difference here in the bottom row that is labeled the main effect of A. Now, when we do that, we see we get negative 40. And so you can see the two values, negative 40, calculated both ways. And so we have two ways for calculating the main effect of A. Similarly, we can calculate the main effect of B first as the arithmetic average of the simple effects of factor B. The simple effects of factor B were found to be 160, and so when we average those, we get 80. All right, this also has a particular location in our two-way table where it's going to go. We're calculating the mean of the simple effects of B, and so that's going to go in that cell right there. So the mean of 160 is 80. We can also calculate the main effect of B as the difference between the means of the two levels of factor B. So mu bar dot 2 minus mu bar dot 1, that would be 140 minus 60, or 80. And so you can see here in the context of the table, we're taking the difference between the two factor level means for factor B, 140 minus 60, and putting that value in that last column labeled the main effect of B. And so when we do that, we get 80. And so you can again see that the two methods for calculating the main effect of B agree. We get 80 in both cases. So we've seen here two different ways for calculating the main effects of A and B. But there's a third way as well. In the notation of the effects model, the main effects are represented as follows. The main effect of A is equal to alpha 2 minus alpha 1, and the main effect of B is equal to beta 2 minus beta 1. And so when we plug in those values, which remember we were given those values for the alphas and the betas in the statement of the example. And so when we plug those values in, we get negative 40 for the main effect of A and 80 for the main effect of B. And you can see that those agree with the values for the main effects that we calculated using the other methods. All right, next let's calculate the interaction effects. And we're going to put the value for the interaction in the bottom right cell of the table. That seems like a good place to put it. And so let's refresh our memory as what an interaction is. The interaction of one factor with another factor can be computed as the difference between the simple effects of the first factor at each of the two levels of the other factor. And so the interaction of A with B is the difference between the simple effects of A. So the two simple effects of A are mu21 minus mu11 and mu22 minus mu12. And so when we take the difference, we get the interaction of A with B. But we can also think of an interaction of B with A, and that would be defined as the difference between the simple effects of B. The simple effects of B were mu12 minus mu11 and mu22 minus mu21. And so if we take the difference, we get what it would be called the interaction of B with A. But now note the following. The interaction of A with B is the same as the interaction of B with A. And in a previous lecture video, we talked about that, and I encouraged you to take these two expressions for these two interactions and show that they are algebraically equivalent. And you can probably just look at them and tell that that's the case. And so that verifies in general that these two interactions are equivalent. They're algebraically equivalent. And so even though we can think, when we have two factors, we can think of the interaction in two different ways. We can think of an interaction of A with B, and we can think of an interaction with B with A, but it turns out that it's the same interaction. Now, in the context of this example, what I want you to do is to verify that numerically they are going to be equal. All right? So in a previous lecture video, I wanted you to look at this in general and show algebraically that they're equivalent. But in this context of this example, what I want you to do is to show that they're equal numerically, given the values that we have. So the interaction of A with B is the difference between the simple effects of A. The simple effects of A were shown to be negative 20 and negative 60. When we take the difference, we get a positive 40. All right, and so here I'm showing the difference between the simple effects of A, negative 20 minus a negative 60, and that gives us positive 40. And then we can look at the interaction of B with A, the difference between the simple effects of B, so 100 minus 60, and that also gives us a value of positive 40. And so if we look in our two-way table, we're taking the difference between 100 and 60, which again gives us a value of 40. So we've verified for this example numerically that the interaction of A with B is the same as the interaction of B with A. So even if you're not able quite yet to see the equivalence of those two expressions, at least we can see numerically that this is certainly the case. So we verified this statement numerically in this example. And so we can see here that there's a common interaction effect between A and B. It doesn't matter whether we look at it as the interaction of A with B or the interaction of B with A, it's the same interaction, has the same value. The value is 40, all right? And that can be calculated either as the difference of the simple effects of A, negative 20 minus a negative 60, or as the difference between the simple effects of B, 100 minus 60. Okay, in terms of the effects model parameterization, we can calculate the interaction of A with B and the interaction of B with A in terms of the effects model parameters. And you can see the expression here. We were given these values in the statement of the example. And so when we plug those in and do the calculation carefully, we see that in both cases, if for both interactions or for both ways of looking at the interaction, we get a value of positive 40. And so again, using these two expressions, we have verified that numerically in this example, the interaction of A with B is the same as the interaction of B with A. And so the interaction of A and B, or the interaction of A with B, we could also call it the interaction between factors A and B, in this particular situation is equal to 40. So we see here that there are a lot of calculations that one can do in calculating various means and effects associated with even a very simple complete factorial treatment structure, just a 2x2, which really is the simplest type of factorial treatment structure. There are three types of effects. We have simple effects, main effects, and an interaction effect. And all of the calculations for calculating the means and the effects can be organized in the context of this two-way table. So I think this is something that you may want to get used to and get familiar with, because it's going to help facilitate doing calculations. Now, what I want to look at next is what's called an interaction plot. And so what I'm doing here, this is a plot of the treatment combination means. And so along the horizontal axis, this would be not a quantitative axis, but a qualitative axis that gives us, or corresponding to the two levels of factor A, so A1 and A2. And then the vertical axis is quantitative, and that is the axis with respect to which I'm going to plot the treatment combination means. And then to correspond or facilitate the two levels of factor B, I'm going to use different colors. So blue corresponds to the first level of factor B, and in this case it looks like it's orange, corresponds to the second level of factor B. And so you can see here that the mean for the treatment combination A1B1, that's equal to 70. The mean for the treatment combination A1B2, okay, that is at 170, and that's a orange point. And then on the right-hand side, I've got the mean for the treatment combination A2B1, a blue point, at looks to be 50. And then the mean for the treatment combination A2B2, that's an orange point, that's at 110. And let me go back one slide. That corresponds to the four treatment combination means in the upper left portion of the table. And then what I've done is I've connected with a straight line corresponding to the color, or using a color corresponding to the level B to connect those points. Now, the reason we do that is because we want to look to see whether those lines are parallel or not. If the lines are parallel, then that would indicate that there's no interaction between A and B. But if the lines are not parallel, as they are not here, then we could look at this and immediately know that there is an interaction between factors A and B. And so what we would be able to conclude then is that because there's an interaction, the effects of factors A and B on the response are not additive. All right? They're not additive because there's an interaction. And so this is a very nice visual way to assess whether or not there is an interaction, and if there is, the degree to which there is an interaction. And it's also a very convenient way to communicate that result once you've determined that. So we can calculate interaction using these formulas that we've looked at. All right, let me go back here. So using any of the formulas on this page, as well as the formulas using the effects model parameters. And if we plot the treatment level means in an interaction plot, we can also look at that plot and determine whether or not two factors interact. So that is the end of example 5.1. We will look at another example in the next lecture video.